Let's jump right into this explainer and trace the incredible physical journey of the subsea umbilical cable. We're going from the surface straight down to the seabed. Think about it. Every valve that opens on a subsea tree, every drop of corrosion inhibitor injected, every electrical signal telling a module what to do, all of it travels down one single cable. These subsea distribution systems, or SDS, are the absolute lifeline between the host facility and the field. If that termination fails, an entire multi-million-dollar field literally goes dark. Before we geek out on the heavy still, the source material draws this amazing parallel to the human spinal cord. Imagine severing just one tiny nerve pathway in your spine. You could instantly lose all motor control in a limb, right? Even if the rest of your body is totally healthy. Which brings us to Section 1, the subsea spinal cord. It's honestly the perfect analogy. Just like your brain controls your limbs through the spine, the topsides facility controls every remote tree through that one umbilical. Remember, a subsea tree sitting thousands of feet underwater doesn't have local power or a hydraulic reservoir. Every single thing it needs to operate has to arrive through this highly engineered distribution chain. And here's what a lot of people miss about how this is built. The umbilical isn't just a giant power cord. It bundles electrical power, high and low hydraulic pressure, chemical injection lines, and sensor data returns all into one armored jacket. So if a termination fails, or you get a single mechanical fault, you can knock out totally unrelated functions all at once. Just like our nervous system, if that one pathway gets compromised, the whole shebang shuts down. Moving on to Section 2, topside to the deep. Let's trace this cable's descent. Starting way up at the host platform, the first thing we hit is the TUT. The topside umbilical termination assembly is this meticulously engineered joint where raw platform power and chemicals actually enter the top of the umbilical. It usually sits right near a J-tube on the deck, acting as a fully enclosed unit housing all the electrical junction boxes and hydraulic block and bleed valves for isolation. Basically, this is where the journey of our subsea spinal cord officially kicks off. Comparing the two ends of the system really clears up the architecture. The tuta up top is consolidating everything to send it downward. Again, think of it like the brain and spinal root. But its seabed counterpart, the suta, acts like a giant breaker panel sitting at the bottom of the ocean, designed to fan those exact same services back out to the individual subsea trees. Let's look at that landing in Section 3, landing on the seabed. Getting a multi-layered cable down thousands of feet and landing it safely on the ocean floor is where the physics get, well, incredibly intense. The subsea umbilical termination assembly is a massive multi-ton structure built around the umbilical termination head, or UTH, and its distribution modules. Landing this beast perfectly is a high-stakes mission. You're fighting unbelievable hydrostatic pressures and the immense hanging weight of the umbilical itself. To actually get this equipment safely onto the mud, installation engineers rely on a highly choreographed sequence called the stab and hinge over. It goes like this. First, they lower the UTH vertically from the vessel. Next, they stab the assembly straight into a mud mat funnel on the seafloor. Then, they gently rotate the whole assembly from that vertical hang into a horizontal resting position. Now, why do it this way? That rotation is absolutely crucial for managing the massive tension in the umbilical. If you just dropped it flat on the seabed or bent it aggressively, the internal tubes and sensitive electrical cables would suffer catastrophic damage. The stab and hinge over ensures the cable isn't crushed or ripped apart at touchdown. Okay, Section 4, connecting the field. So the suta is firmly seated and fluids are ready to flow. Now we have to physically connect this hub to the wellheads. Two main connector families do the heavy lifting down there in the dark. First, you have the MQC, or Multiple Quick Connect, which couples several hydraulic and chemical lines simultaneously in a single stab. And second, the HFL, or Hydraulic Flying Lead, which is a discrete, flexible jumper routing service to just one individual tree. Let's break down how they work together. MQCs give you incredible speed and reliability across multiple circuits, so you use them to connect the suta's distribution modules directly to the main trunk lines. HFLs are more like your final, flexible extension cords, reaching out into the dark ocean to deliver services to specific remote wellheads. And of course, making those final HFL connections requires an ROV, a remotely operated vehicle to do the actual physical hookup. Which brings us to the tricky part. Section 5, the margin for error. Because let's be real, things on the ocean floor rarely match the blueprint perfectly. Put yourself in an installation engineer's shoes for a second. You've executed a flawless stab and hinge over. Your suta is down. But then, your as-built seabed survey shows your target's subsea tree accidentally landed, say, 3 meters further away than the design drawing assumed. What exactly happens to your hydraulic flying lead?
Well, the reality of seabed metrology is brutal. If you didn't design your flying lead with a generous slack margin to account for this positional tolerance, your cable simply is not going to reach. Period. Actual measurements on the ocean floor are never perfectly as planned. And the cost of getting that wrong is staggering. A short or misaligned flying lead is one of the most common early life faults in a subsea field. If it's too short, you have to refabricate it and send a second vessel out to install it. And get this, that vessel mobilization alone can cost well over $100,000 a day. You are quite literally bleeding money because a cable was a few meters too short.
The source material puts it perfectly. Marine installation sequences are fundamentally irreversible in real time. Once a multi-ton structure starts descending through the water column, there is no pausing physics. You can only monitor and respond. So generous tolerance bands and meticulous planning aren't just good practice, they are absolutely vital to financial survival. Ultimately, the big takeaway from this explainer is that subsea distribution is all about anticipating the unpredictable. We aren't just talking about clean, perfect designs on paper. It's about surviving the harsh, irreversible physics and the messy metrology of the deep ocean. When you think about it, every single successful umbilical termination is a massive triumph of engineering over an extreme environment. So I'll leave you with this to chew on. If a single, vulnerable cable lying in the freezing dark holds the entire fate of a massive offshore energy field, what other hidden lifelines are silently powering our modern world right under our noses? Keep questioning, keep learning, and I'll catch you in the next explainer.